Search bar is a common feature on many websites. Where there is a need to interact with a database, there you have a search bar. A basic search bar with a simple algorithm as matching the input string with a substring of a database is quite simple to implement. But a search bar with an autocorrect feature goes a long way in enhancing the user experience. In this video, I'll explain the algorithm behind the spell check algorithms and go through the code which will be helpful for you to integrate in your websites. Let's kick things off by understanding how the spell check algorithm recommends you the words. Now, the spell check algorithm recommends you the words which have the least cost. That means the distance or closeness between the search input and the dictionary of words. This cost can be quantified by the number of operations required from transforming from one word to another. Generally, a character can be converted to another with three methods, either addition, deletion, or substitution. The algorithm involves by comparing the last characters. If they do match, in this case which they are, then the cost of the characters becomes the cost of their heads. Here, head is the substring of a word without the last string. In the case where the last characters do not match, then we check three conditions. In the addition condition, we first convert the input string to the head of the designated string and add the last character. Hereby assuming A as the input string and B as the designated string, which becomes the cost of A, head of B plus 1. In the deletion case, we delete the last character of the input string, which returns as the head of the input string, and then we convert to the designated string. This is 1 plus cost of head of input string, B. In the substitution case, we convert the last character of the input string to the last character of the designated string, and then convert the heads. So basically, we'll get the designated string here, which becomes 1 plus cost of head of input string, head of the designated string. Thus, we can rewrite this algorithm with the non-recursive parts included like this. The actual Levenstein distance algorithm uses tails instead of heads, but this algorithm is quite inefficient. Thus, we'll use an improved version developed by Wagner and Fischner, which uses a matrix-based approach to get the distance between the strings. Let's start by constructing the matrix with the rows representing the input string and the column representing the data, with A and B as the input and the word. Let's take the example for the conversion of a string pthen, which is obviously incorrect, to Python. We fill the boxes like this and add a small hyphens at the start representing the nil strings. Now the conversion from nil string to another nil string takes 0 operations since technically they are the same. The conversion from a nil string to a p requires an addition, thus the cost is 1. And the conversion from a nil string to py, which is the third box we are looking at, requires 2 additions, thus the cost is 2. And we'll fill up the other boxes in the similar fashion. The conversion from p to a nil string requires 1 deletion, which is we have to delete the p. Thus the cost is 1. Similarly, the conversion from pt to a nil string requires 2 operations, that is 2 deletions. Thus the cost is 2. Thus we'll fill out the non-recursive steps like in this way. Let's consider the second box in the second row here. Now the cumulative strings from the both sides will be p and p. If the n characters are equal, then the cost of both the cumulative strings will be equal to the cost of their heads. Thus, the cost of p, equals cost of head of p, head of p, which is cost of nil string, nil string, which is 0. Now let's consider the other box. In this case, the end strings do not match. The cumulative strings are p from the input string and from the above one, which is py. If the n characters do not match, the cost becomes 1 plus the minimum of the addition case, deletion case, and the substitution case. The cost in the path of addition is 1 plus cost of p, head of py, which is cost of p, p. Thus we take the value from the left box and then add 1. For the deletion case, it is the cost of head of p, py. This is the cost of nil string, py, which is the upper box plus 1. For the substitution case, it is 1 plus cost of head of p, head of py, which is the value in the diagonal box plus 1. We'll fill up the values here and take the minimum. Thus, to summarize, if the costs for addition, deletion, and substitution were to be 1, we pick the minimum of the 3 boxes, the left box, the upper box, and the diagonal box, and add 1 if the end strings do not match. Let's redo the case wherein the instincts match. If the instincts match, the cost becomes the cost of their heads. The cost of their heads is the value in the diagonal box. Now thus we fill up all the boxes in a similar fashion, checking whether the instincts match or not, and filling the values until the last box is filled. The final result is the value in the lower right box. Just to cap things off, the addition direction is towards right, +1. The deletion step is from top to bottom, which is +1. The substitution case depends on the end character. 0 when they match and 1 if else. That means they do not. If you want to customize, you can customize the weights for addition, deletion, or substitution. I'll be using NumPy here. It's not necessary, but it'll be helpful. Let's define the function named getDistance with the argument search input and word. Let's define a and b as the lengths of the inputs. Define the weights of addition, substitution, and deletion as 1, 1, 1. Let's initialize the distance matrix with all the zeros in it. The shape must be a+1 and b+1 because an additional blank is added. Let's add the non-recursive parts or cells. The distance matrix colon, 0 represents leftmost column, and the distance matrix 0 represents the first row. The leftmost column will be corresponding to the search input, and the first row will correspond to the word. Let's check the output by printing the matrix. Let's use the same example I've used before, PTHEN and Python, and we can see that all non-recursive parts have been initialized correctly. Let's get into the recursive steps here. We'll initialize 2 for loops for I in range 1 to a+1 and j in range 1 to b+1. Now the I represents the row number and the j represents the column number. To get the end characters of 2 words, we will use search input I-1 and word j-1 to compensate for the additional blank we added at the start. If they match, then the value in the current box, which is distance matrix I, j, will be equals to the diagonal box, which will be I-1, j-1. If the end characters do not match, then we'll take the minimum of the addition case, which is left box, means I, j-1 plus the addition weight. The deletion case, I-1, j plus deletion weight, and the substitution case, I-1, j-1 plus substitution weight. Well, that should complete the algorithm, and we'll return the last elements of the matrix a, b. Thus we'll get the same result 2 for PTHEN to PYTHON. If we change the E in PTHEN to O, then we will get the answer as 1 because it will need only one addition. And let's just see how much time would it take to run this algorithm. Let me import time and do this. Let's just say you want to implement a search bar like an autofill. Let's just say if you want the results to be recommended, even when the user did not type in completely, then you can subsidize the cost if the search input is a substring to the word. We can do this by adding if the search string or search input is in the word, then we will return 1/4 the cost it would have been come from the matrix here. Thus we can see if I input HE and HELLO, instead of returning 3, it returns 0.75.